Hello and welcome to Principles of Mathematics lesson number 19. In this lesson, we're going to learn about proportional reasoning. We will look at the following items: ratios, proportions and their properties, constant of proportionality, and scaling. Starting with ratios, a ratio is basically what we use to compare quantities in mathematics. Uh, a ratio is usually written either in this form, A to B, using a colon between the two. The order matters, of course, because a ratio can also be written as a fraction, A over B, and we know that division is not commutative, so A divided by B is not the same as B divided by A, so we have to be very careful about the order in which we write the ratio. Ratios are used to represent part-to-part, part-to-whole, or whole-to-part comparisons. Let's look at a couple of examples to make this really make sense for us. Okay, so there were 7 males and 12 females in the Dewdrop Inn on Monday evening. In the game room next door were 14 males and 24 females. In the first part, we want to express the number of males to females at the inn as a ratio. This would be a part-to-part comparison. So we want basically the ratio of males at the inn to the females at the inn. So the number, of course, of each of those. So we know that there were 7 males and 12 females, right? So the ratio is basically 7 over 12, which we can, of course, also write as 7 to 12. Now, whenever we're dealing with a ratio, if there is any reducing that's possible, any simplification of that fraction, we always want to do that and give this in the simplest possible form. Now, in this case, 7 and 12 are relatively prime, so they don't have any common factors we could divide off, so therefore this would be our final answer. Next, we want to express the number of males to females at the game room as a ratio. This will also be a part-to-part comparison because we're not dealing with the total number of individuals in either scenario, so that's why they're both part-to-part comparisons. So here we're going to look at the number of males at the game room, which we'll denote by mg, to females at the game room, which we'll denote by f sub g, right? So we notice that there are 14 males and 24 females. So this will be 14 over 24. Recall that we always want to reduce if possible. We notice that 2 is a common factor, so we can divide off the 2 on both of them and we get 7 over 12. So even though the numbers were different, notice that the ratios are the same. We can of course write this second one as 7 to 12 as well. All right, so we're dealing with the same scenario, but in this case, we want to express the number of males in the game room to the number of people in the game room as a ratio, and this will be a part-to-whole comparison. So notice that in the game room, we have the number of males in the game room plus the number of females in the game room, giving us the total in the game room, right? So we have 14 males plus 24 females for a total of 38. So the total number of people in the game room was 38. So the ratio of the number of males in the game room to the total number of people in the game room would be 14 over 38, which we will reduce because we can divide both top and bottom by 2 to 7 over 19. which we can of course write as 7 to 19 in that format. All right, one of the most important types of equation in mathematics is that of a proportion. A proportion is nothing but a statement of equality between two ratios. So if I have one ratio A over B and another ratio C over D, if I make the statement that A over B equals C over D, this is called a proportion. And we've already seen equations of this type, and if you recall, of course we need to indicate that neither B nor D should be 0 because we cannot divide by 0, and we've already seen why this relationship holds true. If you recall, we refer to this as the principle of cross multiplication. Of course, if you're given this, it's very easy to see why this ends up being true. We've seen it before, but real quickly we'll go over it again. So we have A over B equals C over D. We go ahead and notice that the LCD for both sides would be BD, right? So we're going to multiply both sides by that LCD. So we have A over B, which we're going to multiply by that LCD, and we'll multiply the right side by the same LCD, BD. We can, of course, do that. It's perfectly legal because we know that we can multiply both sides of an equation by the same number. In this case, that number being this product of B and D. And that's called the multiplication property of equality, right? So notice that now the B's cancel out on the left side of the equation and the D's cancel out on the right side of the equation. And we end up with AD equals CB or BC, right? So therefore, we go ahead and state that therefore AD is equal to BC. Again, we refer to this as the principle of cross multiplication, a very useful relationship which helps us solve proportions when one of the four quantities is unknown. All right, once you really grasp the concept of proportions, they're going to become one of your best friends because there are countless many scenarios in life you can actually apply the notion of proportions. Here we have Carl that can type at 8 pages for every 4 pages that Dan can type. If Dan has typed 12 pages, how many pages has Carl typed? Now, given the tool of proportion, this becomes an extremely simple problem to solve. Firstly, do note that this is a multiplicative scenario, given that the speed of one person is basically twice the speed of the other, right? So that twice indicates a multiplication relationship or a multiplicative relationship. So here we can set up a really simple proportion. So we're going to say 8 pages for Carl corresponds to 4 pages for Dan. So now we want to know 12 pages for Dan. So what we'll do is just we'll put it at the same level we had the 4 pages for Dan. Corresponds to how many pages for Carl? See, that simple proportion helps us solve this equation very, very quickly. So at this point, we'll go ahead and utilize the very useful principle of cross multiplication, which we just learned. At this point, I'll go ahead and drop the C's and the D's. This was just to help us make sure that we're putting the right item in the right spot, right? So now we can put either cross product that we want on the left of the equation that we're going to write and the other one on the right. So I'll just put the one containing the x, so 4x. Remember, 4x and 8 times 12, they're called cross products. So I'll put this cross product 4x, and that's going to be equal to 8 times 12. Now, a lot of people have the habit of going ahead and multiplying that out, but I encourage you not to, and you'll see in a second why. Because at this point, to solve for x, we're going to divide both sides by 4, right? Notice that it's a lot easier if you leave it as a product of 8 and 12 rather than writing 96 to see how cross-canceling is going to be possible now. So I notice that these 4's on the left will cancel out, and on the right, the 4 and the 8 leave you a 2 on the top, right? So now we can see that x is equal to 24. So if Dan has typed 12 pages, that means Carl could have typed 24 pages in the same time period. All right, so that's how simple these can be handled. Or simply, I should say. So once again, remember, when you have A over B equals C over D, AD and BC are called cross products. So we say if A over B equals C over D, then the cross products are equal. Here we have another example. Ali and Bente typed at the same speed. When Ali has typed 8 pages, Bente has typed 4 pages. When Bente has typed 10 pages, how many has Ali typed? Now, this example is put here precisely to make you aware of the fact that even though this may sound like a multiplicative relationship, it's actually not, because remember, they're typing at the same speed. So the number of pages that, for example, one types in a given period of time is going to be exactly the same as the others. So what you want to do is make sure that you don't try to set this up in the way we set up the previous example. Now remember, they're typing at the same speed. So Bente has typed 4 pages, and we want to know when Bente gets to 10 pages where Ali is going to get. So remember, for Bente to go from 4 pages to 10 pages, that means they've had an additional, what, 6 pages, right? So all you're going to do is start with the 8 pages that Ali was initially at, and just add the 6 pages to realize that, oh, okay, at this point, she has typed 14 pages. See, the big error to watch out for is to make sure you don't do the following proportion. 8 for Ali to 4 for Bente, because this is not true. Remember, they type at the same speed. So therefore, if in the given time that Ali does 8 pages, Bente is also going to do 8 pages. So this is a real situation to be careful about and not to fall for. So make sure that you can handle this and understand it before we proceed. It is not impossible to use a proportion for these. The fact is that it would be kind of a trivial proportion, because you would say, okay, here, starting from 4 pages, Bente has typed 6 extra pages. So you want to know 6 pages for Bente corresponds to 6 pages for Ali, would mean how many pages for Ali correspond to 6 pages for Bente? See, it's like a kind of a very trivial type of proportion you would have to set up, right? And then you would realize, oh, that's also going to be 6 pages, right? So x becomes 6, and therefore you add the 6 to the 8 and you get 14. So you see, this is why you really don't want to go here, because it's unnecessary, right? So remember, this is just an additive relationship. You just, you go from 4 to 10. So how far is this one going to go? From 8 to 14, just add 6, right? So be careful. All right, so here we have another perfect situation to use proportion. If there are 3 cars for every 8 students at a high school, how many cars are there for 1,200 students? Please pause and see if you can set it up yourself, then come back. All right, welcome back. Notice that 3 cars correspond to 8 students, right? Remember, those subscripts are just there to help us remember what these quantities refer to, and also to set up our proportion correctly. So on the other side, we want 1,200 students corresponding to how many cars. Just put the students at the same level you have students in this ratio. So 1,200 students correspond to how many cars? The point being that this ratio doesn't change even though the quantities change, right? So when the quantities do change, they change according to the same proportion. So here all we have to do is just go ahead and solve this simple proportion. We'll go ahead and put this cross product 8x and set it equal to 3 times 1,200. So now we're solving for x. Remember, you don't want to multiply that out. It's easier if you leave it as is. So we're going to divide both sides by 8. So notice that these 8s on the left will cancel out. Now, you could obviously use a calculator to figure this out, or multiply it out by hand. But if you're clever, you can actually avoid the use of a calculator. Watch, because we can break that 1,200 up. We know we can at least break it up as 4 times 300, right? Well, that's getting us closer to be able to cross cancel it with 8. So we'll do one more trick, and we'll write it as 3 times 4, and we'll write the 300 as 2 times 150. See? Convince yourself that these two are the same, right? In fact, that this 3 times 1,200 and this expression 3 times 4 times 300 and this expression 3 times 4 times 2 times 150, they're all the same, right? Now watch how we can cancel out the 4 times 2 on the top with the 8 on the bottom. So now all we need to figure out is 3 times 150, and of course 3 times 15 is 45, so we just add a 0 to get 450. How many cars are there for 1,200 students? So we just answer what? 450. 450. There you go. One concept closely related to our notion of ratios and proportions is the concept of direct proportionality and the constant of proportionality. So if one variable x and another variable y are related in such a way that y is just some constant which we call k times x, then we say y is directly proportional to x, and k in this case will be called the constant of proportionality. Now, there is another way these are referred to, so I just want to point it out in case you hear it, you know that they're the same thing. Instead of saying is directly proportional to, we could have said varies directly as x. So if you hear that, if you say y varies directly as x, it has the exact same meaning as to say y is directly proportional to x. And k in that case would be called the constant of variation rather than proportionality, but they have the exact same meaning. All right, so let's look at an example. We're given that y is directly proportional to x. We're also given that the value of y is 8 when the value of x is 5. Then we want to first find the constant of proportionality. Then we want to find the value of x when y equals 12. And finally find the value of y when x equals j. Okay? So the first thing we'll do is we'll go ahead and write down the equation of proportionality. In this case, it's y, which is directly proportional to x. So we get y equals some constant times x, right? And given the fact that we know this relationship, that y is 8 when x is 5, that helps us go ahead and find the constant of proportionality. So we put 8 for y, the k we don't know, we just keep it as k, and then times 5. Now we solve this simple equation for k by dividing both sides by 5. So we end up with k equals 8/5. Now that we have k, we can write the proportionality relationship as such: y equals 8/5 of x. So this is the fixed relationship between these two variables, y and x. Now I can solve any scenario they throw at me like this. Find the value of x when y equals 12. So all we have to do now is replace y with 12, and we get 12 equals 8x over 5, and I'm going to write the 12 as 12 over 1. This is so that I realize, oh, here I'm just dealing with a proportion, right? So I can, of course, invoke the principle of cross multiplication. I'll write the cross product of 8x times 1, which is 8x. And that's going to be equal to 12 times 5, which is 60, but I'll just write 12 times 5 because I'll be able to simplify more effectively that way. Now I'm going to divide both sides by 8. Now I do notice that the 8's cancel out on the left side, but on the right side, 8 and 12 have a common factor of 4. I know that 4 goes into 8 twice when it goes into 12 3 times. So we get x equals 15 over 2. All right, so this will be the answer for part B. This, of course, the constant of proportionality was the answer to part A. For part C, we want to find the value of y when x equals j. So for part C, we go ahead and again start with our proportionality equation. Given that we know k, we go ahead and use this one. So y equals 8/5 x. So all I'm going to do is replace x with j. So I get y equals 8/5 j. And there is the value of y when x is j. So that's how you handle these direct proportionality equations. Basically, when two quantities are directly proportional, their values go up together or they go down together, okay? And that's that. To help you understand what I mean by quantities go up together or down together when they're directly proportional, I want to look at a real simple example, say y equals 2x. So we have a simple direct proportionality between y and x in this case. And if we just make a table of values and look at some typical values indicating the relationship between y and x, you'll see, for example, if x is 1, then y is 2 times 1, which is 2. If x is 2, y is 2 times 2, which is 4. If x is 3, y becomes 6. 4, y becomes 8. Notice that as the values of x increase, so do the values of y. Or you can look at it in the other direction, as the values of x decrease, so do the values of y, right? So they go up together, they go down together. That's what we're talking about with respect to direct proportionality. Also happened, and notice that this is always happening at the same ratio of 2 to 1, right? Or 1 to 2, depending on which way you're looking. 1 to 2 if you're looking at the relationship, the ratio of x to y, and 2 to 1 if you're looking at the a ratio of y to x. So this is what I was referring to. I just wanted to make sure that's clear before we proceed. All right, there's one strategy called the scaling strategy, which can be helpful when trying to find, for example, which of certain types of buys is the best buy. In this case, we'll use the scaling strategy to determine which is a better buy. 12 tickets for $15 or 20 tickets for $23. Now, the way we do that is by basically finding out if there's a certain quantity we can aim for, which can easily be reached, and then finding the price for that common quantity. Now notice that 12 and 20 have a least common multiple of 60. So if we can find out how much of each of these scenarios will cost for 60 tickets, then we can see which one is better, which is a better buy. Now, we know that 12 tickets here cost $15. So to get the value for 60 is very easy because 12 times 5 is 60. So we simply multiply the 15 by 5, we get 75. So here we know that 60 tickets will cost $75 in the first scenario. So 12 for 15. Now we'll do the same thing for the other scenario, 20 tickets costing $23. So of course, if we want 60 tickets, we're going to multiply the 20 by 3. So we'll do the same to the 23, we get 69. So you can see that in the first scenario, the 60 tickets would cost you $75, but in the second scenario, the 60 tickets, which is the same number of tickets, therefore comparable, would cost you $69. So of course, this second plan is the one that is the best buy. So that's one way of finding the best buy. There is another way which I actually prefer and recommend to you, and that's using the unit rate. Let's look at that. To find the unit rate, you basically take each scenario, like for example, 12 tickets for $15, and you find the unit rate. In other words, the dollar amount for one unit. So be careful, make sure to put the right number on the top. Here we want to put $15 over 12 tickets. Now, in order to get the unit rate is very simple. Basically, we're going to divide both the numerator and the denominator by 12 because we want to get the price for one ticket. So, of course, when we divide 12 by 12, we just get 1. So that'll just be one ticket. And now we're to drive 15 by 12, all right, which we'll do on our calculator. So 15 divided by 12. And that'll give us 1.25. So, all right, so this is called the unit rate for the first scenario. So that means the cost of one ticket, right? That's what we mean by unit rate. Then we do the same for the second scenario, which is 20 tickets for $23. So 20 tickets for $23. Again, make sure you put the dollar amount on the top and then the number of tickets on the bottom. So now we want to make the 20 tickets become 1, so we're going to divide by 20, right? So we're going to do the same to the 23, right? So we take 23 and we divide it by 20, we get 1.15. So This is really a nice strategy because you have now the unit rate for each. You know how much each ticket costs. So there's no better way to determine which one is a better buy than doing that. And of course, because you're looking for a better buy, you want to know which one is going to cost you less, right? So this vendor is obviously giving a better deal. So we'll go with that vendor. That's how you find the best buy using the unit rate strategy. Notice that when we were dealing with ratios, right, the ratio that we would end up with always was unitless, right? It was just a pure numerical comparison of two quantities. If you want to have units involved, such as in this case, you have dollars per ticket, etc., then you no longer use the term ratio. That's when you use the term rate, okay? So the rate of change of one quantity with respect to another quantity. All right, let's look at one more problem. Kai, Paulus, and Judy made $2,520 for painting a house. Kai worked for 30 hours, Paulus worked for 50 hours, and Judy worked for 60 hours. They divided the money in proportion to the number of hours they worked. They all earned the same rate of pay, and we want to know how much did each earn. So this is a scenario in which we don't know the rate at which they worked, right? So we'll go ahead and give it a name. We'll call it X. Which is the pay rate, right? Which is how much they made per hour, right? And notice that the pay rate, which is the amount of money that they made per hour, times the number of hours would give the dollar amount that each made, right? So, for example, for Kai, we know that if we take the rate, which is X, and multiply it by the number of hours, which is 30, that would be 30X, right? So this is how much Kai made. And of course, if we do the same thing for Paulus and Judy, we will see that 50X will be the amount that Judy made, right? And 60X would be the amount that, 50 was for Paulus. So 50 was the amount that Paulus made, and 60X would be the amount that Judy made, right? So we know that if we take all these amounts and add them up, we get the total amount that was paid, right? So there is where the equation is going to come from. So 30X plus 50X plus 60X should equal to, let me actually move that. All right, that's better. So that's going to equal to the 2,520. So now we just need to solve this simple equation to get the rate at which they were, the equal rate at which they were all getting paid, right? So 30 plus 50 is 80 plus 60 is 140. So we get 140X is equal to 2520. So we divide both sides by 140. And the 140 is on the left, cancel out. Therefore, we get X equals, now we're just going to do this simple calculation. 2520 divided by 140 So we get 18. So that means they were getting paid at $18 per hour. And remember, that was the rate each of them was getting paid at. And now, if we want to know how much did each earn, all we have to do is realize that Kai made 30 times that X. So Kai made for Kai, we multiply 30 times 18. So 30 times 18, so 540. And for Paulus, we're going to multiply the 18 by 50. So I believe that's 900. Yeah, 900. And for Judy, we're going to multiply 60 by 18. And we get 1,080. All right, so that's how we would go ahead and approach a problem like that. All right, so make sure you can handle something like that on your own before we proceed. Okay, one type of application in which proportions come in really handy is when we deal with scaling, such as this problem. The floor plan of the main floor of a house in the figure is drawn in the scale of 1 to 300. So basically that means the actual size for each side of each room in this building is 300 times what we're seeing, right? We want to find the dimensions in meter of the living room. So what we could do is we could actually turn the scale into a meter scale, or just do that at the end, which is, I think, the better method. So let's go ahead and here's the living room. Let's go ahead and find the actual sizes. So we set up a very simple proportion here. We say 3.7 in the model. Remember, we do the subscripts just to help us remember. They're not actually there. Is to what actual size in the actual building as 1 is to 300. So that's the simple proportion that's going to get us the result that we need. So now we just solve this simple proportion using cross multiplication. So we get x times 1, which is x, equals this cross product, which is 300 times 3.7. So we go ahead and calculate that. So 300 times 3.7. So we get 1,110. Now, we know that that's going to be in centimeters, right? But they want the answer in meters. So what we do is we simply use a nice unit factor. A unit factor is a fraction where the numerator and the denominator are basically referring to the same quantity. So we know that since I want the centimeters to cancel out and leave me meters, I'm going to put my relationship between centimeters and meters in such a way that centimeters end up on the bottom and the meters on the top. Now, what's the relationship between centimeters and meters? That's easy because we know there are 100 centimeters to 1 meter. So now we go ahead and realize that the centimeters cancel out. You have to make sure your units always work out properly. And all I gotta do is divide 1110 by 100, and I know that just moves the decimal 2 places to the left, right? So this is going to be 11.10, which is just 11.1. Remember, you don't need to write the trailing zeros at the end of a decimal. So we get 11.1 meters. Okay, so that's one of the two dimensions. Now we do the same thing for the other side, which is represented by 2.5 centimeters on this model, right? So we now say 2.5 centimeters on the model represents to what value on the actual building or house, given that the ratio of the model to the actual house is 1 to 300. So again, we end up with x equals 2.5 times 300. So we know that's going to be 75, I believe. Let's go ahead and make sure. So 2.5 times 300, it's 750. I have my decimal one off. So 750. Now remember, that's in centimeters, right? So we're going to use a scale factor again, or a unit factor, to convert. So we know again 100 centimeters corresponds to 1 meter. Centimeters cancel out. So I get, I know that dividing by 100 moves the decimal 2 places to the left, so I get 7.50, which is just 7.5 meters. So the dimensions of the living room are basically 11.1 meters by 7.5 meters. That's how we state the dimensions of a rectangular figure, right? Usually length by width. So width is usually the shorter of the two, etc. So that's how we do a problem like that. All right, here's a good problem. We have that the ratio of 8th graders to 7th graders at a meeting is 4 to 7. If 1/4 of the 8th graders are boys and 2/7 of the 7th graders are boys, what's the ratio of boys to students at the meeting? All right, and then we're given the number of boys and we want to know what's the total number of students. Now, the first way that I'm going to show you is the proper way, which will help you figure this out even if the numbers don't work out in a nice way, as I'm going to show you they do in this one. So this is a special case where the numbers actually work out in a way that you can do a clever trick, and I'll show you that next. But first I want to show you the proper way. The proper way is we just use the knowledge of ratios and proportions that we've learned. So we know that the ratio of the 8th graders, let me call the number of 8th graders E, and let's call the number of 7th graders S, right? So we know that the ratio of 8th graders to 7th graders is 4 to 7. Now, one thing we could do is we could go ahead and solve this equation for one of those two variables so that we only deal with one variable when we try to get a total rather than two. So if I just multiply both sides by S, notice that we end up with S is canceling out on this side, and we end up with E equals 4/7 S, right? Now, I would like to get an expression for the total number of students at this meeting using what I just discovered, okay? So I know that the total number at the meeting is going to be E plus S, right? So since I want to use just one letter, I'm going to actually replace E with 4/7 S. So I get E equals, instead of T is equal to E plus S, and instead of E, I'm putting 4/7 S plus S. Now I can simplify that further, right? Because remember, I can just think of the 1S here as 7/7S, right? So now I have two fractions with the same denominator, so 4 plus 7 is 11, so I get the total number is 11/7 S. Now I want to figure out the total number of boys. I know that it's 1/4 of so the total number of boys is going to be 1/4 of the 8th graders plus 2/7 of the 7th graders, right? Again, remember, we want to be able to work with one variable to make life easier for ourselves, right? So what we're going to do is, once again, we're going to replace E with what we found it to be over here, which is 4/7 S. So we get 1/4 times 4/7 S plus 2/7 S, correct? So that's going to be the total number of boys. And I notice here that the 4's here cancel out. So we end up with 1/7 S plus 2/7 S, right? So if I add those, because they have the same denominator, that's easy. So I get 3/7 S. And that is the total number of boys. Okay, so now I have an expression in terms of S for the total number of boys, and we have an expression in terms of S for the total number of students at the meeting, right? So if we want the ratio of boys to the total number of students, all we now have to do is find the ratio of B over T, which is going to be, remember, B is 3/7 S and T is 11/7 S. Do notice that the S's cancel out to give us just a pure proportion, a pure ratio. Remember, ratios are unitless, okay? So now all I gotta do is take care of 3/7 divided by 11/7, which I know from the rules for division of fractions. I keep the 3/7, turn the division into multiplication, and then I look at the multiply by the reciprocal of 11/7, which is 7/11. So we end up with the ratio of boys to the total being, notice the 7's cancel out, so we get 3/11, or we can write it as 3/11, like so. All right, so that's the first part. All right, now they tell us, okay, assume there are 9 boys at the meeting. Then they want to know what's the total number of students. So we know we have an expression for boys here. So if I just plug in 9 here, that's going to give me the number of 7th graders once I solve the equation. So I get 9 equals 3/7 S. Think of it as 9/1 equals 3S/7, so that it becomes a proportion. Now we can cross multiply, so we get, therefore, 3S equals 63. So S equals, divide both sides by 3 and you get 21. Okay, so we have 21 seventh graders. Now we can easily find the number of 8th graders because we know that's going to be 4 seventh S, right? So the number of 8th graders is going to be 4 seventh times that 21, because remember E equals 4 seventh S. We know S now, so 4 seventh times 21, that's going to give me, these are going to cross cancel, leave me 3, so 4 times 3 is 12. So now I know the number of 7th graders and I also know the number of 8th graders, so now we can easily add those to get the total. So the total is going to be 21 plus 12, which is 33. So that's the total number of students at the meeting. All right, so this is, in fact, the proper way of handling this, so that if the numbers don't work out as nicely as I'll show on the next slide, you can still handle it. So this is the general approach for a problem like this. Now I'll show you the clever approach, just because of the fact that these numbers work out so nicely. So notice that we know that the ratio of 8th graders to 7th graders is 4 to 7. So we have 1, 2, 3, 4 blocks here and 7 blocks here, right? Now, we know that 1/4 of the 8th graders, so we shade 1 of these 4, and 2/7 of the 7th graders, so we shade these 2 over here from the 7th graders, are boys. So what's shaded now is the number of boys, right? So if we want to know the ratio of the boys to the total number, we have to take the 3 and divide it by the total number of blocks we have here, which is 11, so we get to 3 to 11. But notice what I meant is that this is working out nicely just because of the way the numbers work out, right? If the numbers didn't work out this nicely, then you would need a more general approach, which is what I taught you in the previous slide. Now, if you want to do the second part, you know that basically the number of the boys is 9, so 3 of these units are equaling 9, so one of these units equals what? 3, so we have 11 of the blocks, so we get 11 times 3 equals 33. Again, a clever way, but not as general as I showed you in the previous slide. All right, this brings us to the end of the lesson proper. Per our usual practice, we'll look at a few homework problems now. All right, here we have an example of a recipe problem where proportions come in quite heavily. So we have a recipe that calls for 1 tablespoon of mustard seeds, 6 cups of tomato sauce, 4.5 cups of chopped scallions, 8.25 cups of beans. We want to know if one of the ingredients is altered as specified, how much of the other ingredients should be changed to keep the ratios the same. So I'll just kind of get you started by doing a couple for part A, and then you should be able to take the rest on your own. So the first thing you want to do is be very organized about your information. So we'll write down the original amounts that are being used. So we know that mustard seeds, we need 1 tablespoon. For tomato sauce, we know that we need 6 cups. For chopped scallions, we need 4.5 cups. And we need 8.25 cups of beans. So here we're organizing the initial information given. All right, so now we want to know, for example, for part A, if we use 2 cups of tomato sauce, how are we going to have to alter the other one? So we're changing the tomato sauce from 6 cups to 2 cups. Okay, so this can be accomplished very easily using proportions. So the way we would set it up is this. So let's start with mustard seed, for example. So we know that the original ratio between them is 6 cups to 1 tablespoon. So here we're taking care of mustard seed, right? So 1 tablespoon. So then all we have to do is say, okay, we're going to alter the 6 cups and change it to 2 cups. So we say 2 cups corresponds to how many tablespoons? See how easy that is? Just like that. So now we just need to solve this simple proportion. Once we go to our equation, we can drop the units and just work with the numbers to make it easier. So we get 6x, we're just cross multiplying. 6x equals 2 times 1, which is 2. Now we just solve for x by dividing both sides by 6. So we get x equals 1/3. So we know that we're going to have to use 1/3, and of course here we're dealing with tablespoons. So 1/3 tablespoon of mustard seed. All right, I'll show you one more. Let's say we want to find out how much chopped scallions we're going to use, right? Now, it's given as 4.5. We know it's a little bit easier to work with improper fractions rather than mixed numbers in calculations. So let me convert that. 2 times 4 is 8 plus 1 is 9. So this is 9½ cups, right? So all we have to do is we start with the same proportion for tomato sauce, 6 cups. But in this case, to what? To 9½ cups, right? For chopped scallions. We want to know what happens to the 9½ cups when the tomato sauce amount changes to 2 cups, right? So we want to know x cups for chopped scallions. Again, we have a simple proportion. We solve it. So 6 times x equals 2 times 9/2. The 2's cancel out, so I just get 6x equals 9. So x equals 9/6, which is the same as 3/2 if we reduce it. Now, you do want to give your answer in the proper format, which in this case is mixed numbers. So you just divide 3 by 2, you get 1, 2 with the remainder of 1. Remember the loop. So we get 1.5 cups of chopped scallions, okay? So just like that, you can figure out all the other quantities as well. Very simple using proportions. All right, let's go ahead and move on. All right, so in this problem, we want to divide 350 in the ratio of 1:4. So basically, we're gonna have a bar model like this, right? Where we have a ratio of 1:4, right? So we know that some multiple of 1 plus the same multiple of 4 should add up to 350. So basically we have 5x. We're just calling that factor that we need x, right? So 5x should equal to 350. So we know that factor should be 70. So all we have to do now is figure out what is 1 times 70 and what is 4 times 70. So 1 times 70 is of course just 70. 4 times 70 is 280. So if we're going to split up 350 in that ratio, it would be 70 to 280, like that. Of course, it is possible to handle this without getting x's involved. So you just have to keep in mind that the total breakup is going to be into 5 pieces. So what you could do is you could say, okay, what is 1/5 of 350? and you would know that that's 70, right? And then don't forget that the other piece is going to be 4/5 of the same number. So 4/5 of 350 will be 4 times 70 according to that cancellation, so you get 280. So there's another way of getting the same answer. This is more of an algebraic approach. This is more of an arithmetic type of approach. All right, that's how you do that part. For the next part, you would do it either this way or that way, exactly the same way, but don't forget that the ratios are different. So there you would have 5 and 4 represented in your drawing, and then you would do 5/9 of the number for 1 and 4/9 for the boys. All right, 5/9 for the girls and 4/9 for the boys. Okay, so that's how you approach something like that. Okay, so here's a problem that uses the concept of similar triangles. We want to know how high is a tree that casts a 20-foot shadow at the same time that an 8-foot post casts a shadow of 4 feet long. So basically, you're looking at two triangles like this. You have a tree casting a 20-foot shadow and an 8-foot post at the same time casting a 4-foot shadow. So this is a known fact from physics and geometry that at the same time, basically, this casting is going to happen in a proportional manner, right? So this is the unknown quantity here, the height of the tree. All we have to do is set up a simple proportion. We say x is to 8 as 20 is to 4. So x over 8 equals 20 over 4. There are different ways you could have set up this proportion. You could have said x is to 20 as 8 is to 4. That would have gotten you the same answer. As long as you're consistent in the way that you set it up. So now we're just going to solve by cross multiplying. So we get 4x equals 8 times 20. We divide both sides by 4. And these cancel out on the left side, so we get x equals, notice 4 goes into 8 twice, so we get 40 feet. So the height of the tree is 40 feet, like so. Okay, here's a question that says if x over y equals a over b, and of course a is not 0 and x is not 0 is true, we want to know what other proportions have to be true. Of course, it goes without saying that b and y can't be 0 because you can't divide by 0, right? So let's take a look at some general facts about this kind of question, then we'll come back to this. All right, so here's some facts about proportions in general. For any rational numbers a over b and c over d, with a not being 0 and c not being 0, a over b equals c over d if and only if b over a equals d over c. In other words, it's a very interesting fact to observe that if you have a over b equals c over d, you want to show that this implies that the reciprocals of those are going to also be 0. Are going to be equal. Now, notice that they specify that a is not 0 and c is not 0, and of course b and d can't be 0 because they're denominators of fractions, and we know that they cannot be 0. So that goes without saying. So we have b over a equals d over c. Now, you can prove something like this quite quickly. Let's go ahead and take a look at why that is true. So we start with A over B equals C over D. And we know that we can cross multiply, right? We know that AD equals BC. Now, I want to prove something that has an A below a B, right? So here's what I'm going to do. I'm going to divide both sides by A because that's going to give me the B over A that I need. That's the first thing we'll do. Now we know we can do that because we can divide both sides of an equation by the same number. All right, now what are we left with? We notice that these A's cancel on the left side and we end up with D is equal to BC over A. Actually, let me write with this other pen. So we get B D is equal to BC over A. Now notice that if I'm trying to prove this, I need a C below the D, right? So now I'm going to divide both sides by C or multiply by 1 over C, the same thing, right? So this implies that 1 over C times D is equal to BC over A times 1 over C. I'm just multiplying both sides by 1 over C, right? So notice on the left side, we end up with D over C. And on the right side, the C's will cancel and we'll end up with what? B over A. So see, that's exactly what we were trying to prove. Of course, B over A equals D over C is the same as D over C equals B over A. So that's when we say QED. You should pause and see if you can prove this other fact yourself. You want to show that if A over B equals C over D, then the ratio of the numerators is also equal to the ratio of the denominators. A over C equals B over D. So pause and then come back and we'll do it together, okay? See if you can do it on your own. Okay, so we have A over B equals C over D, right? We're going to start the same way. We're going to cross multiply BC. Now, we want to prove a fact about A over C, right? So we're going to divide this side, at this time, both sides by C instead of A. So we get AD over C equals BC over C. Now, notice that the C's here will cancel out, so we end up with AD over C is equal to B, correct? Now, notice that since I want to also have B over D in my proof, I'm going to go ahead and multiply both sides by 1 over D or divide by D, the same thing. So let's multiply both sides by 1 over D. The reason I'm multiplying by 1 over D rather than dividing by D is that it'll be easier to work on this side because this is a fraction already. And I know that dividing by D and multiplying by 1 over D are the same operation, so I'll use that fact. So we end up with B times 1 over D. Now notice that on this side, the D's will cancel out, so we'll end up with A over C is equal to B over D, which is exactly what we were trying to prove. So again, we can say QED, meaning that which was to be shown. Okay, so interesting facts about proportions. And that's why in that problem with the casting of the shadows, I told you you could have set it up a different way, because once you have a proportion, a lot of different possibilities coming. In fact, there are other ways you could set these up as well. I'll let you think about some of those. Now we can go back to our problem. All right, so now they're going to give you this proportion and they're going to ask you to see what other proportions will be true. They'll give you a number of choices. I'm going to let you handle that on your own, because now you know what kind of relationships are possible. Just to give you a hint, we already proved that, for example, the reciprocals are going to be equal. So y over x, for example, should be equal to b over a. We already showed that the ratio of the numerators and the denominators should be the same. So x over a should be equal to y over b, etc. Okay, you should be able to handle this now with no problem. All right, let's go ahead and look at one more problem together before we call it a day. All right, we know that we want to know which of the following two recipes will create a juice that will taste more orangey. We're given that 2 cups of, the recipe A uses 2 cups of orange concentrate to 3 cups of water, and recipe B uses 5 cups of orange concentrate to 6 cups of water. This is a problem where the scaling strategy that we saw before works really well. So what we do is we can go ahead and find out what's the common denominator, I mean the least common multiple of these two, 5 and 2, that's 10 cups. So let's see how much water with 10 cups of each of these recipes we'll use. So for the first one, we know that 2 cups of concentrate goes with 3 cups of water. So if I want to see how much 10 cups of concentrate goes with, I just have to multiply the 3 by 5, right? So I get 15 cups of water. Whereas this one, you have 5 cups of concentrate, which goes with 6 cups of water. And we want to know 10 cups of concentrate goes with how many cups of water. So here, since we doubled the 5, we're going to double the 6, so we get 12 cups of water. And of course, given that when using 10 cups of concentrate in both cases, this one uses less water, right? So that means this is going to be more what? More orangey than this one. Of course, if we wanted to, we could have used the unit rate method as well. So it's just that with these numbers, this scaling strategy works a little bit easier. But we could have said, okay, so the recipe A uses 2 cups of concentrate for 3 cups of water. So let's find the unit rate, meaning find out how many cups of concentrate it'll use for 1 cup of water, right? So we just, if we want to get a 1 down below, we have to divide by 3, so we get 1 cup of water. And on the top one, we would have to divide by 3 as well, so we get 2/3 of a cup, right? So for recipe B, we have 5 cups of water, or a concentrate, to 6 cups of water, right? So if I want to get the unit rate on that, in that case, I would want to know how much corresponds to 1 cup of water. So I'm dividing the 6 by 6. I would have to do the same to the 5. So I get 5/6 of concentrate. So looking at it this way, we want to see which one is larger here, the 2/3 or the 5/6. So when I compare 2/3 and 5/6, of course, if I write the 2/3 so that it also has a denominator of 6, that would mean I would have to double both 2 and 3, so I get 4/6, right? So I can say this is 4/6 cup of concentrate with 1 cup of water. And of course, once again, we can see that this one will be more orangey, so because for the same amount of water, it has more concentrate used, okay? So it doesn't matter which way you approach it, you should get the same answer. In this case, we want to see which one has more concentrate. In this case, we're focused on, because the amounts of concentrate are the same, we want to see which one uses less water. So be careful how you approach it, but either way, you'll get the correct answer. All right, so that should do it for today. You take care of yourself, and we'll see you for the next video.